is the 9th video dedicated to Bessey Shuffle diagrams. As a reminder, a shuffle S is said to be a Bessey Shuffle if and only if S preserves or inverts Bessey sequences. Recall, the Bessey sequences of order 8 are 1, 0, 0, 1, 0, 1, 1, 0, and its inversion 0, 1, 1, 0, 1, 0, 0, 1. Also, recall that the two sets of position values of importance to us are the following. Positions 1, 4, 6, 7, which we will color code black, and positions 2, 3, 5, 8, which we will color code red. When cards that begin in positions 1, 4, 6, 7 end up in these same positions after a shuffle is completed, and the same thing for 2, 3, 5, 8, if the cards within these positions stay within those positions, then we say that that Bessey sequence is preserved, and it's denoted as follows. On the other hand, if the cards that began in positions 1, 4, 6, 7 move to positions 2, 3, 5, 8 in some assignment, then we say an inversion of the sequence has occurred, and we represent it this way. Finally, recall that our Bessey sequences 1, 0, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 0, 1, 0, 0, 1 each satisfy one or the other of these two cases here. So in the first case here, the ones are in positions 1, 4, 6, 7, and the zeros are in positions 2, 3, 5, 8. For the inversion of this sequence, the role of zeros and ones switch places. Today we have 4 special shuffles in the study of cyclic and mirrored structures. The first one is called an alternate Klondike, and we will be stacking the left pile on top of the right. So let me go ahead and demonstrate this shuffle. As always, we begin with our ordered packet 1 through 8, and we perform our shuffle, and then we take a look at the new ordering. So what is an alternate Klondike? Well, this is where you hold the cards in biddle grip, it's called, and then you perform a Klondike shuffle type action. So you pull off the top and bottom card as 1, you set it down into a left pile, and then you take the top and bottom card off as 1 and set those two into a right pile. Top and bottom off as 1 into the left pile, and then the remaining 2 cards get set onto the right pile. And since we are stacking left on right, we will get the following new ordering. We get 3, 6, 1, 8, 4, 5, 2, 7. Expressing this outcome in Cauchy's 2-line notation, we obtain the following. The top row, as always, is numbered 1 through 8, and the bottom row is 3, 6, 1, 8, 4, 5, 2, 7. Converting this to cycle notation, we obtain the following. We see that 1 goes to 3, so we have an arrow from 1 to 3. 3 goes back to 1, so we have an arrow returning to 1. So this constitutes a 2-cycle, also called a transposition. Those two just switch places. Next, we see that 2 goes to 6. We have an arrow from 2 to 6. 6 goes to 5. There we go. 5 goes to 4. So we have an arrow from 5 to 4. 4 goes to 8. There we go there. And 8 goes to 7. And we have an arrow from 8 to 7. And then 7 returns back to 2. So it cycles around. giving us a 6 cycle. Color coding our numerals, we obtain the following. Recall position values 1, 4, 6, 7 are color-coded black, and position values 2, 3, 5, 8 are color-coded red. So we see that black 1 goes to red 3, which returns to black 1. Red 2 goes to black 6, which goes to red 5, which goes to black 4, which goes to red 8, which goes to black 7, which cycles around to red 2. So we see that each value gets sent to a value of the opposite color. And when this happens, inversion has occurred. Consequently, if we use our quintessential Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0, and perform the alternate Klondike in which the left pile is stacked on top of the right, it should invert this sequence. So why don't we go ahead and check that. So remember the alternate Klondike, you're pulling the top and bottom off as 1, setting that down on the left, top and bottom off as 1 on the right, top and bottom as 1 on the left, and the final 2 go on the right. We're stacking left on right, like so. So do we get the inversion of that original Bessey sequence? Well, we do indeed. We get 0, 1, 1, 0, 1, 0, 0, 1. Now, it is important to note that all of the cards here have moved from their original locations, right? So, for example, we know that the card originally in position 1 and the card originally in position 3 have switched places. So essentially, that card labeled 0 used to be where this one is right here. And that card right there with the 1 used to be on top. And a similar kind of thing is happening with all of the other cards. They are genuinely being moved around in such a way that 1s and 0s switch places. Also note that this shuffle is of order 6, since we have a 2 cycle and also a 6 cycle. So it would require performing this shuffle 6 times to return the packet to its original order. Let's go ahead and take a look at the shuffle diagram for this shuffle. So top row on the left, we get the following. And as you can see, it's quite a messy looking shuffle here. So we know that 1 and 3 switch places. So what that means then is we should have a double arrow from 1 to 3, and we do. Now look at what 2 does. 2 goes to 6, which goes to 5, and then to 4, and then to 8, and then to 7, and then back to 2. So if we begin at 2, we go down to 6, and then down here on the right to 5, straight across to 4, up here to 8, down to the left to 7, and then straight across to 2, completing that cycle. So that is our 6th cycle, and we say that the values 2, 6, 5, 4, 8, 7 constitute an orbit, which simply means they move around among themselves, and also the values 1 and 3 form their own orbit. Now, I have something here on the top left that we have not seen before. So if you have studied the Hidden Structures online course, you'll be familiar with the following diagram. So let me just go ahead and draw it. So let's say we have 2C. That stands for 2 cycles. And this is cycle with a capital C. So these are 2 cycles in the study of cyclic and mirrored structures. M is for mirrored. And then we have A, M, P. Stands for adjacent mirrored pairs. And then there is an arrow from there up to 2 cycles. So what I am pointing out for all 4 shuffles today is that the alternate Klondike in the case of 4N cards or 4 and objects. So in other words, we're talking like 4, 8, 12, 16, and 20, etc. The alternate Klondike in all 4 of these cases today will convert a 2-cycle structure, as studied in the Hidden Structures online course, to mirrored structures, and these same alternate Klondike shuffles will convert mirrored structures to AMP structures, and they will also convert AMP structures to 2-cycle structures. Now, I do want to emphasize that this is extremely rare, that you can find a single shuffle that will convert between all 3 structure types. It just cycles around. That rarely happens. So in that sense, the alternate Klondike is a very special shuffle. Our next shuffle is again an alternate Klondike, but this time we will stack the final 2 piles right on left. Okay, so let's go ahead and demonstrate this shuffle using our ordered packet. So we have 1 through 8. So we're going to perform our shuffle and then take a look at the new ordering of the cards. Okay, alternate Klondike. Remember, this is where you take the bottom and top card off as 1, set the first pair down on the left, bottom and top card off as 1, set that down into a second pair on the right. Top and bottom is 1, and then there's only 2 cards remain. So you just do this left, right, instead of a regular Klondike shuffle where you're stacking them onto a single pile and building it up 1 level at a time. Now, this time we're going to stack the right pile on top of the left, okay? And as you would guess, this is going to lead to a different order than stacking left on right. So what is the new ordering that we get? We get 4, 5, 2, 7, 3, 6, 1, 8. Writing this in Cauchy's 2-line notation, we obtain the following. Top row is always 1 through 8. Bottom row is 4, 5, 2, 7, 3, 6, 1, 8. And we can convert this to cycle notation as follows. Note that 1 goes to 4, so we have an arrow from 1 to 4. 4 goes to 7, so we have an arrow from 4 to 7. And then 7 returns to 1, so it cycles around, completing a 3-cycle. 2, what happens with 2? 2 goes to 5, so we have an arrow from 2 to 5. 5 goes to 3, so there you go. And then 3 returns back to 2, so it cycles around, giving us a second 3-cycle. 6 goes to 6, so it's a fixed point. So whatever begins in position 6 will return to position 6 once this shuffle is completed. The same thing for position 8. 8 goes to 8. Whatever begins in position 8 will end in position 8. Color coding the digits, we obtain the following. Recall that the 2 distinct sets of position values of importance to us in the study of Bessey sequences are the following. The set consisting of position values 1, 4, 6, 7, and they are color-coded black, and its complement, the position values 2, 3, 5, 8, and we color-code those red. And after the shuffle is complete, one of 2 things will happen. Either the Bessey sequence is preserved or it is inverted. So here we see that black 1 goes to black 4, which goes to black 7, which wraps around to black 1. Red 2 goes to 5, which goes to red 3, which wraps around to red 2. Black 6 goes to itself, and red 8 goes to itself. So we see here each value gets sent to a value of the same color. And when that happens, we say that the Bessey structure of the sequence has been preserved. So there's no inversion of the sequence in this case. And we should be able to readily confirm that by working with our Bessey sequence 1001, 0110 and performing this shuffle. So what should happen is it should return this packet back to its original form as a Bessey sequence. So let's go ahead and perform the shuffle. Remember, top and bottom come off as 1. Set that down on the left. Top and bottom off as 1. Set down on the right. Top and bottom on the left. Last two on the right. We're stacking right pile on top of the left. Okay, so we're expecting to see the same 1001, 0110, which we do. And all of the cards labeled with zeros and ones have actually moved to new locations except for the 1 in position 6 stays in position 6, and the 0 down here in position 8 stays in position 8. Those are fixed points. The other values are being permuted among their digit values of either 0 or 1. Taking a look at the shuffle diagram for this one, so top row on the right, we can see our fixed points of 6 down here and 8 up here, and then we know that 1 goes to 4, 4 goes to 7, 7 returns back to 1. So if we begin at 1, there will be an arrow from 1 down to 4, from 4 up to 7, and then from 7 back to 1. So that completes a 3 cycle. We also say that the values 1, 4, 7 are members of the same orbit. Those values just move around among themselves according to the direction of the arrows in our diagram. Similarly, 2 goes to 5, 5 goes to 3, 3 goes back to 2. So if we come down here to 2, there's an arrow from 2 down to 5, from 5 up to 3, and then 3 straight up to 2. That completes our second 3 cycle. And those 3 values constitute their own orbit as well. I guess I should point out that value 6 here constitutes its own orbit, meaning it doesn't go anywhere, and the same thing for 8. It's an orbit that consists of just one value or one number. And as indicated up here, inversion does not occur. And as mentioned earlier for the previous shuffle, I have some special notes here, top left, pointing out how special the alternate Klondike is, because it's one of very few shuffles that will convert a 2-cycle structure to a mirrored structure, to an AMP structure, and then back to a 2-cycle structure. And I need to emphasize that when we refer to 2-cycle structures here, we're referring to the 2-cycle structures studied in the Hidden Structures online course. And they are always written with a capital C for 2-cycle, whereas when we talk about cycle notation and perhaps a 2-cycle or a transposition, we always use a lowercase c to keep those two concepts separate. So this will make sense to those who have looked into the Hidden Structures online course. And this diagram is true provided that we have 4n cards or 4n objects. Our next shuffle is shuffle 35, the bottom row on the left. This is a judicious Klondike. So this begins the same as the previous 2 shuffles. The only difference is that we will be dealing out pairs into 4 piles, and then we will consider different ways of stacking those piles, which will result in different permutations. Okay, so let's go ahead and derive the permutation for this shuffle. So we begin with our ordered packet 1 through 8. So how this works for the judicious Klondike is we take the top and bottom off as 1 and we put them into a first pile. So like pile 1. Top and bottom off as 1 into a second pile. Top and bottom off as 1 into a third, and then the last 2 go into their own pile as a fourth pile. Now the stacking is as follows. 1 goes on top of 2, that set of 4 goes on top of 3, that pile of 6 goes on top of 4. So in other words, we just stack from left to right. That's all that means. Okay? So what is the new ordering of the cards once we've performed all of those actions? Well, let's take a look. It's 1, 8, 2, 7, 3, 6, 4, 5. So in Cauchy's two-line notation, we obtain the following. The top row is always 1 through 8 in our case. And now we have 1, 8, 2, 7, 3, 6, 4, 5 for our new ordering. This can be converted to cycle notation as follows. 1 goes to 1, so it's a fixed point. So whatever begins in position 1 will stay in position 1 or be returned to position 1 once the shuffle is completed. 2, what happens with 2? 2 goes to 8, so we have an arrow from 2 to 8. 8 goes to 5, so we have an arrow from 8 to 5. 5 goes to 3, so an arrow from 5 to 3. And 3 returns back to 2, completing a 4 cycle, we call it. What else? 4. 4 goes to 7, so we have an arrow from 4 to 7. And then 7 returns back to 4. So this completes what we refer to as either a 2 cycle or a transposition. And finally, 6 goes to itself, so it is a second fixed point. It's also called a 1 cycle. Color coding, these 8 values, we obtain the following. Recall that the 2 sets of position values important to us in the study of Bessey sequences are the following. Positions 1, 4, 6, 7, which are color-coded black, and positions 2, 3, 5, 8, which we will color-code red. If after completing a shuffle, the cards that began in these positions, 1, 4, 6, 7, return to these positions in some assignment, they may have been permuted among themselves. Similarly, if the cards that originally began in positions 2, 3, 5, 8 get returned to those positions, then we say that the Bessey sequence that we're working with has been preserved. Whereas, if what begins in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8 in some assignment, then we say the sequence has been inverted. So we're looking at an inversion of the sequence, and it's denoted as follows. So we see here that black 1 goes to black 1, red 2 goes to red 8, which goes to red 5, which goes to red 3, which returns to red 2. Black 4 goes to black 7, which returns to black 4, and then black 6 goes to itself, returns to itself. It's a fixed point. So we see that each value gets sent to a value of the same color. So what that will mean then is the Bessey sequence we're working with will be preserved. The sequence form of that Bessey sequence will be preserved. So no inversion has occurred here. And we can demonstrate that using our Bessey sequence 1001, 0110 as a starting sequence. And we'll perform this shuffle, and we should get this exact form back once the shuffle is completed. So let's go ahead and just verify that. Okay, so this is the judicious Klondike, where we're setting out pairs into 4 piles. So the top and bottom come off as 1 into a second pile now. Top and bottom off as 1 into a third pile. And then the remaining 2 cards become a 4th pile. The stacking, as indicated here, is from left to right. Now what we're expecting to see is the same sequence form 1 0 0 1 0 1 1 0. And is that what we get? 1 0 0 1 0 1 1 0. So this sequence form has been preserved by the judicious Klondike with stacking from left to right. And I have a note up here for those who have studied Principles in the Hidden Structures online course, that this judicious Klondike is a very special shuffle in the case of 4n cards. So that would be 4 cards, 8, 12, 16, 20, 24, and so forth. For packets of those sizes, this shuffle will convert what we call a two-cycle in the study of cyclic and mirrored structures. It will convert that structure type to a mirrored structure, and then convert that to an AMP structure, and then convert that back to a two-cycle structure. And it is extremely rare to find a single shuffle that will complete this cycle. Normally, only certain shuffles can be used to go from one structure type to another. But here we have found a shuffle that works for the completion of that diagram. So let's go ahead and look at the Bessey Shuffle diagram for the judicious Klondike, in which we're stacking left to right. So this is shuffle 35. So as already indicated, we do have two fixed points, 6 and 1. Objects in those positions are returned to those positions. And then because we have a transposition right here, 4, 7, that means we should expect to see a double arrow between 4 and 7, which we do. And then we have a 4 cycle here. 2 goes to 8, which goes to 5, which goes to 3, which wraps around to 2. So if we go down here to 2, we should see an arrow from 2 up to 8, which we do. An arrow from 8 down to 5, and then an arrow from 5 to 3, and then an arrow straight up to 2. And that completes the 4 cycle. We also say that those 4 values, 2, 8, 5, 3, constitute an orbit, since they are values that simply get moved around among themselves according to the direction of the arrows in the diagram. And we also have a smaller orbit of just 2 objects, 4 and 7. And then we have 2 very small orbits, one consisting of just the number 1, and another orbit consisting of the number 6. Our final shuffle for this video is shuffle 36, bottom row on the right. This is also a judicious Klondike. So it's a dealing out into 4 piles by way of the Klondike shuffle. But this time we will be stacking from right to left. And so we'll show you how to read that notation in just a moment. So let's go ahead and begin with our ordered packet 1 through 8 and perform our shuffle and see what new ordering results. So the judicious Klondike, this is where you take the top and bottom cards off as 1, put them down into pile 1 here, top and bottom off into pile 2, top and bottom off into pile 3, and then the last 2 constitute pile 4. Now the stacking is as follows. 4 goes on top of 3. That set of 4 will go on top of 2. That bigger set of 6 will go on top of 1. Now all that means is we're stacking from right to left. That's just a way to notationally represent the stacking of these 4 piles from right to left. Okay? So what is the new ordering we obtain? Well, it's 4, 5, 3, 6, 2, 7, 1, 8. Expressing this in Cauchy's 2-line notation, we obtain the following. The top row is always 1 through 8. In our case, the bottom row is 4, 5, 3, 6, 2, 7, 1, 8. We can convert this to cycle notation as follows. 1 goes to 4, so we have an arrow from 1 to 4. 4 goes to 6, so we have an arrow from 4 to 6. 6 goes to 7, so we have an arrow from 6 to 7. And then 7 returns back to 1, so it cycles around, completing a 4 cycle. Next, 2. Where does 2 go? 2 goes to 5, so we have an arrow from 2 to 5, and then 5 returns back to 2, so that completes a 2 cycle, also called a transposition. 3. 3 goes to 3, so we're looking at a fixed point. So whatever begins in position 3 will be returned to position 3 once this shuffle is completed. And finally, 8. 8 is also a fixed point. So whatever begins in position 8 will return to position 8 after this shuffle is completed. If we color code our values, we obtain the following. Recall that the sets of position values of interest to us in the study of Bessey sequences are the following. The first set consists of 1, 4, 6, 7, which we've color-coded black, and position values 2, 3, 5, 8, which we've color-coded red. In the case that the Bessey sequence is, quote, preserved, this represents that outcome, or if the sequence is inverted, then this represents that outcome. And just to remind you, an inversion occurs if the cards originally in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8 in some assignment, and vice versa. But looking at the color coding of our cycle notation here, we can see that inversion has not occurred because we have black 1 going to black 4, which goes to black 6, which goes to black 7, which wraps around to black 1. Red 2 goes to red 5, which wraps around to red 2. Red 3 gets assigned to itself. Red 8 gets assigned to itself. Now, one thing you may have noticed if you've gone through many of the videos in this series dedicated to Bessey Shuffle diagrams, if we've ever had a shuffle that has a fixed point, where a card in one of the positions always returns to that position, if it is a Bessey shuffle, it must be that the Bessey sequence form was preserved, as is the case here. In fact, let's go ahead and just demonstrate that. So if we begin with the Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0, and perform this shuffle, we should get this same sequence form back. So let's check that. So the judicious shuffle in which we stack from right to left is as follows. You take the top and bottom off as 1, put them down for the first pile, top and bottom off as 1 for a second pile, top and bottom off as 1 for a third, and then the last 2 become a fourth pile. And then we're stacking from right to left. Okay? And what we're expecting to see here is the same sequence form of 1, 0, 0, 1, 0, 1, 1, 0. And that is what we have here. Now, even though we get back to this Bessey sequence organization, it doesn't mean that the cards have not moved around, right? Because we know that most of them have moved around. Okay, so for example, the cards in positions 1, 4, 6, 7 have been moved around among themselves, which are the locations of the ones. Remember, the ones begin in position 1, 4, 6, 7, so those are moving around among themselves. Similarly, the 0 in the second position and the 0 in the fifth position switch places every time you perform this shuffle, whereas The 0 in the third position right here, this one right here, it stays there. It's a fixed point. Similarly, the 0 in the 8th position over here stays there. So 6 out of the 8 cards are genuinely moving around each time you perform this shuffle, even though the net effect is we get back to our original sequence form of 1 0 0 1 0 1 1 0. And finally, if we take a look at our last shuffle diagram, so bottom row on the right, we observe the following. We know that value 3 and 8 correspond to fixed points. And I want to remind the reader that normally when we write cycle notation for a permutation, the one cycles or single cycles are typically not written down. And you can do that as long as you are aware of the size of the set of objects you're working with. So as long as we know we started with 1 through 8, you can safely drop these one cycles. Now down here we included them just to show you that the color coding makes clear that every value is returned to a value of the same color. Okay, so back here, so once again, fixed points 3 and 8. Now look at what happens with 1. 1 goes to 4, which goes to 6, which goes to 7, which wraps around to 1. So if we come over here to 1, we should have an arrow from 1 to 4, which we do. We should have an arrow from 4 to 6. There it is. And then we should have an arrow straight up to 7. And then we should have an arrow from 7 back to 1, completing that 4 cycle. And so those 4 values, 1, 4, 6, 7, constitute an orbit, as does the 2 values 2 and 5. That's an orbit of 2 objects. And then we actually have 2 tiny orbits consisting of just 1 value each. 8 constitutes its own orbit, as does 3. And before we leave Shuffle 36, let me just point out Shuffle 36, as indicated down here. Now, of course, now you can't read it. Shuffle 36 is the inverse of Shuffle 12 at the bottom of the screen. It's also identical to Shuffle 15. So why don't we just quickly take a look at those. Okay, so going back to Shuffle 12, the claim is that this shuffle here, the mange under over, is the inverse of Shuffle 36. Now we've seen this kind of thing before, where earlier we saw that the mange over under is the inverse of Shuffle 19. That was a Klondike shuffle, if you remember. So boy, I don't know how many people would believe that the mange under over and this Shuffle 36 actually undo each other. That is really difficult to believe. But look, you can take advantage of that fact. So let me just demonstrate that it's the case. So if we begin with an ordered packet 1 through 8, if I perform the mange under over, which is one we've covered already, this is where you move the top card into your other hand, and then the next top card goes under. We're going to do this alternating under, over, under, over. So it goes under and then over, under, over, under, over, under. Okay, so we get quite a mess here, as you'll see. Okay, now amazingly, because we've just shown it here, the shuffle diagram for the mange under over is identical to the shuffle diagram for Shuffle 36, except for the fact that the arrows go in the opposite direction. And that indicates that these must be inverses. Okay, so we've performed the mange under over. So let's go ahead and perform the shuffle that we've just introduced, Shuffle 36, and apparently it will undo the effect of the mange under over. Okay, so Shuffle 36, one more time here. So you Klondike one pair into like a pile 1, Klondike a pair into pile 2, Klondike a pair into pile 3, The last two go down as pile 4. And then remember, for shuffle 36, we're stacking from right to left. Okay? And the claim is, because these are inverses of one another, we should get the original ordering of the cards. So I challenge really anyone. Watch the actions of the mange under over. Watch the actions of shuffle 36, the judicious Klondike, where you're stacking from right to left, and see if you can draw the conclusion that those two shuffles undo the effect of each other. Okay? And since we have inverses, that also means that we could perform shuffle 36 first, followed by the mange under over, and it will still reset the packet to its original order. Okay? So I thought I'd point that out. And then also you'll see that at the bottom of shuffle 36, there's a statement that that shuffle is identical to shuffle 15. Okay, so what was shuffle 15? Shuffle 15 is just the ordinary Klondike. Isn't that interesting? Now this won't be as hard to see, I don't think. But this is the ordinary Klondike where you're stacking them on top of each other. In fact, if you think about shuffle 36 being equivalent to this one, it won't be as big of a leap to see that shuffle 36 should be the inverse to the mange under over. Okay? So why is this? Why are these two identical? Well, what does the Klondike Shuffle do? This is where you take the cards, top and bottom off as 1. Okay, this is the first pair set down. Top and bottom off as 1. This is the second pair being set down. Top and bottom off as 1. Third pair, last two go on top. Isn't that the same action as doing this, which is what shuffle 36 is? Where the bottom pair will be on the bottom. This will be the next pair up. This will be the next pair up. And then this will be the top pair of the pile if you stack from right to left. Okay, so I think that one can be puzzled through and detected that, oh yeah, shuffle 15 truly is the same permutation as shuffle 36. Okay, so let's do an application. I have here 8 cards. As you can see, I have 2 6s, 2 7s, 2 8s, and 2 9s, all scrambled together. Okay, so we're going to perform each of our shuffles today, and if you were here, I'd have you tell me which one would you like me to do first, so I'll just have to kind of randomly choose one. So maybe we'll do 34 first. So that's an alternate Klondike. This is where you stack, you deal out into a left pile and then a right pile by way of the Klondike Shuffle. And for shuffle 34, we're stacking the right on top of the left. Very good. Maybe you'll ask for shuffle 36 next, let's say. So this is a judicious Klondike. So here we're Klondike shuffling pairs into 4 piles, and the stacking in shuffle 36 is from right to left. Okay, very, very good. And let's see, why don't we do the alternate Klondike 33, shuffle 33. This is where we deal left, right, but this time we stack left on top of right. Okay, and the last shuffle we haven't done yet is shuffle 35, which is where we deal pairs to the table into 4 separate piles, like so, using the Klondike Shuffle. And here we're stacking from left to right. Now rest assured that if you were here, we could perform these 4 shuffles in any quantity and in any order. In fact, we can perform any of the shuffles that we have shown you in this series as many times as you like and in any order that you would like. That's the amazing thing. Okay, so what I'm going to do here is just mix the cards further. If you think about it, we've been mixing cards into piles of 2 and 4. Well, maybe we should go ahead and deal out the cards into 3 piles, which is what I've done here. Okay, so this will just further scramble the cards. And now what I want you to do is I'm going to deal the cards into 4 piles again, but in the shape of a square, which kind of is fun. So where would you like this one? Top right corner, directly below, and this one up above, and then this one. What about this one? Want it over here, up there, over there, and then over here. Okay, tell me how you'd like these stacked. This one first, okay. Which one next? Bottom right, bottom left, and then top right. Okay, very good. Now I want you to feel comfortable with all of the mixing here. So what I'd like you to do is just cut the cards wherever you would like. That way I could not possibly know where you're going to cut the cards. So maybe you cut the cards right there, and we put the bottom on top. That's a cut. Okay, now from here we're going to just deal into 2 piles, and I have off to the side a prediction I wrote that's been in plain sight the whole time. So what is the prediction here? The 6s hate the 7s, and the 8s can't stand the 9s. What does that mean? Well, we've put them into 2 groups here, 2 piles of 4 cards. This is claiming that no pile should have both a 6 and 7 in it, and no pile should have both an 8 and 9. Ooh, is that even possible? Let's check this out here. What about this pile? There's a 6. Ooh, these better not be 7s here. 8, okay, that's fine. Oh, 6 is fine with 6. Oh, yes, 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 yes. Okay, so it looks like, yes, indeed, the 6s and 7s stayed away from each other. What about the 8s and 9s? Did they stay away from each other? They did indeed. These 2 groups just separated like oil and water. I think there's some truth to these statements here. I don't think the 6s like the 7s, nor do I think the 8s like the 9s, and we have just shown it. Isn't that amazing? That prediction was written before all of the randomization choices were made, and it was shown to be true. Wow, how is that even possible? Okay, well, let's take a look at how that is even possible. Okay, well, there's so many ways that you can kind of set this up if you would like. An easy way to go is go ahead and just stick with the 2 sets that we have. Remember our prediction. We don't want the 6s and 7s together in any way. We don't want the 8s and 9s together in any way. Okay, so if you set up these disjoint little piles here and have as your plan, this will be 1 pile at the end, and this will be a 2nd pile at the end, then our prediction will come true. Okay, so what we're going to do is I'm going to take either of these sets of 4 and then just set them on top of each other. Okay, now this is pre-performance setup. Okay, so you would create those 2 blocks of 4 where you're wanting those blocks of 4 revealed in the end. Now we already know a very clever technique from taking this organizational structure where you have the top 4 you want to keep together and the bottom 4 you want to keep together. If you do this triangle deal, do you remember that? This is Werner Miller's genius idea. If you perform this clockwise triangle deal and then pick up the first pile first, but now stack in counterclockwise direction, it will convert what we just had to a Bessey sequence. Okay, a Bessey sequence. Okay, so how do we see that? Well, it gets a little tricky to see. That's why I suggest that you use Werner Miller's little technique for converting it. But if you think about it as like a 1 0 0 1 0 1 1 0, where are the ones? And are they safe to put together? Well, let's say this is a 1 here. So 1, 0, 0, 1. So we have a 7 and a 7 as a 1. Now remember, it's then 0, 1, 1, 0. So we would see that the 7s here would be paired with the 9s. And putting the 7s with the 9s is safe to do. It's the 6s and 7s that don't get along. It's the 8s and 9s that don't get along. Okay, so the remaining cards that could be represented by zeros would be the 8 and 6, and then over here, the 6 and the 8. And those are safe to put together. So if you just take a few moments and study that structure, you'll realize that this is a Bessey sequence relative to those two disjoint sets of values. Okay? Now, once it's a Bessey sequence, we know that it's invariant or unharmed by any of the shuffles that we've shown you thus far, and in particular, the 4 shuffles we demonstrated today. So you can go ahead and perform any of these shuffles. Why don't we just do 2 of them? Why don't we do 33? But you can perform any of these, in fact, any of the 36 shuffles. See, shuffle 33, we're stacking left on right. Okay, and then why don't we do one of the judicious Klondikes? What about 36? So this is where you put out pairs into 4 piles, like so. And now the stacking for shuffle 36 is from right to left. Okay, so we'll just do 2 of them, but this is still a Bessey sequence. Okay. Now, as an extra credit note here, performing 33 and 36, have we inverted this? Has it technically become, instead of 1001, 0110, is it now 0110, 1001? Well, look, it has, because shuffle 33 inverts the sequence, whereas shuffle 36 does not. So this has been inverted once. Of course, if we were to invert it twice, you get back to the original sequence form. But whether this is inverted or not will not undermine the conclusion in any way. Okay, so we have a Bessey sequence here. Okay, now if you remember, what I did next is I actually did that triangle deal. I kind of justified it and said, well, we've been dealing into 2 piles and 4 piles. Poor number 3 is feeling left out. So why don't we deal into 3 piles? Well, that's all a guise, really, because what I'm needing to do is use Werner Miller's clever little procedure for converting this back to a packet structure where the top 4 are of the kind that we want in one pile. You can see that. Remember, the 6 and 7s don't like each other, and the 8s and 9s don't, okay? And then here, the other half is 7s and 9s. Those are safe. They don't mind each other, okay? So performing Werner Miller's triangle deal on this kind of structure, which is what we had at the beginning, converts it to a Bessey sequence. And then if you perform that same triangle deal a second time, it converts it back from a Bessey sequence to this kind of arrangement. Okay? And then from there, I claimed that I was going to perform a square deal. It sounds kind of fun. We just did a triangle deal. Why don't we do a square deal? So this is where I had the spectator, and these are free choices. I had them tell me like where to put these. We're going to create a square shape. Okay, very good. Where would you like this one? It truly is a free choice, which is amazing. This could go there, this one could go there, and then look at this. You can pick these up in any order. It won't hurt anything. Okay, and we talked about why you can do that in an earlier video in this series. So you may want to make note of that. But we can actually pick these up in any order. And let me just tell you what structure we have now. I guess I can show that. It's not too hard to see. This is going to be an cyclic construction. It's going to alternate these 2 sets of cards. Now remember, the 6s and 8s are okay together, and the 7s and 9s. So what's going to happen is these will alternate relative to set membership in the 2 sets where you have the 6s and 8s together and also the 7s and 9s together. So this is kind of like having red, black, red, black, red, black. It's an alternating cyclic construction. Okay, so when you have something like that, you can freely cut it without harming that organization. We could have actually performed a Charlier shuffle if we wanted. This is where it's top to bottom, bottom to top, top to bottom. I have a separate video on the Charlier shuffle that you may want to look up to learn this shuffle. It's really just equivalent to cutting the cards just once at some location, which is quite surprising and hard to believe actually, but it is the case. So here we have like a red, black, alternating structure. So from this point, all I need to do, if we're wanting like all the reds in one pile and the blacks in the other, is just alternately deal them, because they are alternating in their membership among those two sets. And so at this point, your prediction's going to be true, where you could bring it out at this point and say, well, I wrote this prediction at the very beginning about the 6s and 7s not getting along, and also the 8s and 9s. Is that actually true? Well, let's see what these sets consist of. Well, the first, oh yeah, there you go. The first pile consists of 6s and 8s, staying away from the 7s. And then the second pile, we know that the 7s, we know that the 8s and 9s don't get along, and they're not found in the same set, so we've kept those two groups of cards that don't get along with each other separate from one another, just as in the original performance. So anyway, that's how you perform that application, and it's just one of countless ones that can be designed once you understand the underlying principles being taught regarding Bessey sequences and Bessey shuffle diagrams. So thank you for watching, and take a look at the next video in this series, which will be the 10th video, and we'll be finishing up this series in just a few more videos, and you'll have a very large list of shuffles that preserve or invert Bessey sequences.